because we don't see any probability words in this title, right? But in group theory, the productivity degree itself means probability. Or if you happen to see any other words like commutativity degree, it also means probability. So let's discuss further on this productivity degree in our next section. So I believe that everyone are very familiar with probability, right? It's a part of mathematics that evaluate the chance of events to occur, and it is expressed as a number between 0 and 1, and an even value 1 can be considered a certainty. But in group theory, if the commutativity degree or probability is equal to 1, it means the group is abelian. So the theory of commutativity degree in group theory plays a major role in determining the abelianness of a group. So, but what does it mean by abelian? So, in this research, we denote a group as G, capital G, and it is called an abelian or commutative if all elements of the group commutes. So we consider for all elements, if they commute to each other, we can say that the group is abelian. So meaning that if you take any two arbitrary elements, X and Y, and you apply the operation of G, let's say X times Y, it is equal to Y times X. But the operation is not necessary to be multiplication. It can be any other operation. It depends on what operation in the group itself. Okay, let me share on some probabilities in group theory. Let's start with commutativity degree. So the commutativity degree is the probability of two random elements X and Y commute, and it is denoted as P of G. This is the notation of the commutativity degree. And the first appearance of this concept was in 1944 by Miller. And it is defined as the following ratio, which is the number of order pair that commute XY equal to YX divided by the total number of order pair in the group. So here you have to take note that XY and YX are two different pairs. So let's say, let me give you an example. Let's say we have 4 elements in a group A, B, C, and D. So we're going to find the total number of order pair of this group with order 4. Okay, then you're going to have the first pair A and A, AB, AC, and AD. And then we'll start with BA until BD. And the last one is D and D. So you're going to have 16 elements here of order pair. But how do we determine this number of order pair that commute? Actually, there are 2 approaches in finding the commutativity degree of a group, but I will just explain the first method, which is by using modified Kelly table, or we would say as 0-1 table. So let's start with, let's construct Kelly table. We use the same table as in construct here. So, to construct a Kelly table, we list out all elements of the group A, B, C, and D along the top row, and this is the top row, and along the left column, and they are listed in the same order from left to right as well as from top to bottom. And let's say the operation in this group is multiplication. So AB, let's say A times B here, and B times A here might be different. Okay, so 0, 1 table is a table in which the corresponding, in which each of the boxes here, corresponding to AB and BA will be placed, will be assigned the number 1 if AB equal to BA. So from this Kelly table, we transform to 0, 1 table, and we gonna replace the number 1 in these two boxes if they are commute, means AB equal to BA. So let's say it depends on the to multiply these two elements. It depends on the representation group of each other. So let's say these two elements commute. So we will assign the number 1 here in these boxes, BA and AB, A times B or B times C. Otherwise, if AB does not equal to BA, we place the number 0 here. So you just calculate how many numbers of the number 1 that we have in these boxes, and then you just substitute into this formula. Divide by 60. For this case, we have order 4. So we have 16 total number of order pair. Okay. And the idea of commutativity degree was then investigated by Erdős and Turan. And the result obtained encouraged many researchers to work in this topic, and various generalization has been done. And next probabilities, we have relative commutativity degree, denoted as P of Hg. Okay. And so this relative commutativity degree is actually the extension from the commutativity degree. So by changing the role of element to subgroups of a group, one can obtain a modification of the commutativity degree. So Erfanian et al. Extend the concept of commutativity degree to relative commutativity degree of a subgroup H of a group G. Now, one element chosen from H and another one from G. So you can see here, the first element here is coming from subgroup H, and the second element here is coming from the group G itself. And divide by the order of H times the order of G. Okay, but now to be a subgroup of a group, you can just think of a subset of a set, but it must satisfy some properties to be a subgroup. Of course, the operation in H must be the same as in G, and then it must be closed, meaning that if you take any two elements, then you apply the operation, then the element you obtain must be in H. And there exists an identity element as in G. And the last one is every element in H has its own inverse. Okay? That is the properties to be a subgroup. Okay, then we have the N commutativity degree is actually a generalization of the commutativity degree for the case N equal to 1. It is just the same as PG, right? When N equal to 1, you will get XY equal to Y, the same as PG. Okay, and this generalization was firstly introduced by Muhammad Ali and Sami in 2010. Okay, and there are many generalization of a commutativity degree, which has been done by many researchers as stated in this table. Okay, we have, as I mentioned just now, Erdos and Turan determine PG for a symmetric group, and then we have another computation by Sami and Muhammad, where they compute for two generated two groups of nil potency class 2, and then we have relative commutativity degree by Efranian et al. And Abdurrani et al. Determine the co-prime probability for P group. Okay, and then we come out with, before that, in this research, we introduce new probability, which called as the productivity degree of two subgroups of a group. Okay, as you can see here, we use the terms productivity degree instead of commutativity degree. Why? Because as you can see here, we have a product of H and K. That is why we use this term productivity degree. And we extend the concept of commutativity degree to two arbitrary elements, one in H and another one in K, where H and K are two subgroups of a group. So we consider two subgroups of a group. And this productivity degree is defined as a ratio of the order of intersection between H and K with the order of their union. So this is the definition of productivity degree of two subgroups of a group. And we focus in this research, we focus only on dihedral groups. So this is the definition of dihedral group by Gallian. And so dihedral group is denoted as DM, is a set of symmetries of regular M-gon. And the order of DM, dihedral group, is 2 times M. And this is the notation or symbol of the order of the header group. And it can be represented in a form of generators and relation given in the following representation. So we're going to apply this representation group to determine the element of the header group for each order. Okay, let's say we want to determine the header group of order 3. D3, when M is 3. So you will be expecting 6 elements because the order of this header group D3 is 2 times 3, right? So you will be expecting 6 elements in this group. But what are the elements? So we'll start with A here. And we multiply one more time A square. And then one more time you'll get A cube. But here, since M is 3, so A cube is equal to 1. Right? So we'll just replace A cube with 1, or 1 is actually the identity element, or we would write as E. This is represented as identity element E. Okay? And then we start with, and then if you multiply one more time, you will get A power 4, right? But A power 4 is equal to A because A cube is identity. And you will keep repeating, get the same element. So we just stop until we get identity element. But now we have P, and B squared is equal to 1. Or identity, we already have identity here, so we don't need to put 2 times. So you will have B only here, and then AB, A square B, A cube B is equal to B because A cube is 1. So no need to put A cube here because we already have B in this set. So these are all the elements of the hierarchy group of order 6. Okay. So this is the Kelly table for the hierarchy group of order 6. We will refer to this table. We will use this table in our next section. So to construct a Kelly table, first of all, the entry here must be an element of group. It cannot be any other element that except the element in the group. So how do we multiply? I think for this part, I think for this part, it's just a straightforward. But I want to show how do we multiply. Let's start with B. Multiply B by, let's say, A. Okay. Before we multiply these two elements, usually the first row here, that correspond to identity. This is the identity that correspond to the identity. Usually the top row must match this row, the hidden row, as well as this column, the left column here, okay, that correspond to this identity must match to the corresponding must match to this heading column. I mean this column. Okay, why? Because identity element commute with all element in the group. That is by property of identity. Okay, so now how do we multiply two elements? Let's say we multiply B and A. Why don't we just put BA here? Because as I mentioned just now, this entry must be element in the group only. So BA is not the element in this group, right? Because just now we obtained, there is no BA here. There is no BA. So by this relation we have here in this representation group, we know that BA is equal to A inverse B. And for this group of order 6, we know that A cube is equal to 1 or identity. So, and if you multiply on the left by A inverse, both sides, you will get A inverse is equal to A square. So BA, since BA is equal to A inverse B, so you just replace A inverse with A square. That is why we have A square B here. Okay, so you may use the same method for other element. For B times A square and so on. Okay. Next, we have another Kelly table, which is Kelly table for direct groups of order 8, because 2 times 4, right? 2 times 4 is 8. Okay, then we come up with one proposition and two theorems. Okay, the first proposition is we consider the case for M is odd. For M is odd, the order of the hierarchy group is 2n. So we consider for the case M is odd. And if the order of H and K is 2, then the probability is equal to 3 over 5. Okay, of course, we have proved the proposition and theorem we obtained, but today I will just present the example to illustrate the results. So we consider a hierarchy group of order 6, D3, Okay. The element in H and K consists of two elements because the order of these two is 2. So they consist of two elements. Let's say for subgroup H, we have EB, element E and B. For subgroup K, we have element E and AB. Then we want to find the intersection between HK and KH. So you have to determine HK first and KH. So HK, you multiply H by K. This is component-wise. You multiply E times E, the first component you have here, and E times AB, second component, and then B times E, you will get B, B times AB, you will get A squared. So you just refer to the previous table. We have table 1 to multiply two elements. Okay, so let's say we multiply B and just now I already show you a B multiply A. Let's say B multiply AB. What will you get? B multiply AB. You will get A. Sorry, this one is actually A cube. No, A square. So since there are three common elements, we have E, A, B, and B. So the number of intersection between HK and KH is 3. Because B times AB does not equal to AB times B. So we only have 3 common elements. And the union between these two is 5 because we have 5 different elements. We add these two, A cube and A. So the probability, you just apply the formula. The intersection, the order of the intersection between HK and KH divided by the order of their union, which is 5. So we obtain this probability, 3/5. So as I mentioned just now, this is applicable for the case M is odd. And for the order of the subgroup H and K is 2. Then the probability is 3/5. Okay, next. Okay, this theorem number 1. If one of the two subgroup is a normal subgroup, then the probability is equal to 1. So we consider, for example, we consider the hydrogen groups of order 8. So this one is a normal subgroup. What does it mean by normal? Normal subgroup. So normal subgroup means every left coset of the subgroup is equal to the corresponding right coset of the subgroup. If we multiply on the left of the subgroup with all elements in the group, then they are corresponding to the right coset. Let's say we have this normal subgroup, right? So if you multiply on the left, so we have how many elements in the groups? D4, 8, right? So we multiply by all elements in the group. Start with identity A until A cube B. Multiply by this subgroup. This we call as left coset. And they are all equal to right coset. Okay, that is why we say this is as normal subgroups. And K is not normal. So again, we determine HK and KH and then find the intersection between these two. Since the element in these two, HK and KH, are equal, so the order of the intersection is equal to egg. Okay, and the union, their union is also X. So that is why we have we obtain the probability as 1. 8 by 8 is 1. Okay, and the last one is theorem number 2. So now we consider, instead of 2n, we want just to make it different between the previous proposition. We use 2p, where p is prime number, and if the order of h, either the order of h or k is equal to 1 or p, then the probability is equal to 1. And meanwhile, if the order of h and the order of k is 2, then the probability is equal to 3/5. So we consider the same group as in our previous example. This is D3, type D3. The group of order 6, and so this h, let's say we consider h as p. Okay, and we refer to the table 1, the Kelly table of order 6, the group of order 6, then you multiply hk and kh, so you will get the same element in these two set, the same element. So the intersection is 6. And of course, the union is also 6. So that is why the probability is equal to 1. And if we choose the order of h is 1, we will get the same result because identity commute with every element. Okay, and the second part here is actually just the same as the in our proposition 1, but this is for prime number. Just now this is for prime number, and that one is for odd. So actually, I just want to combine these two so that so that we have one theorem for this part. Okay, so I think that's for the conclusion. So in this research, the productivity degree of two subgroups has been obtained for direct groups, and from the result, we have probability. We have shown that the probability is equal to 1 if H is a normal subgroup, and if the order of either the order of H and K equal to 1 or P, for the case P is prime, and the productivity is equal to 3/5 if the order of H and K is equal to 2 for the case M is odd. Okay, that is all from me. Thank you.
Okay, thank you, Dr. Mohaniza. Now, question and answer session. For those who have a question, please deliver your question now. Maybe Prof. Hamidin, you have a question maybe? For the viewer or follower from the YouTube channel, you can ask your question from chatting box, and our committee will manage your question. Okay, anyone have a question?
Yeah, may I ask questions, Doctor?
Yeah, sure.
Thank you. So these are your PhD degree results, or just you are giving something which you are dealing with?
Yes, a part of my PhD research.
Oh, I see.
That is a yes.
Because why I'm just focusing on this, because theorem number 1 is trivial.
Yes.
Why trivial? Because if you have normal subgroup of any group, then if you multiply it by K, then another group. Theorem number 1, yeah. You can see here in your particular case, in your particular example 2, you have HK is KH. If I am not mistaken, if you have normal subgroup, any normal subgroup, then HK is KH. So this is a subgroup. This is the first thing I should do, take into account. So secondly, since HK equals KH, then that means intersection, number of elements of intersection and the number of elements of union will be the same. So that's why in this case it's the trivial. How you prove that any theoretical proof for theorem 1? Do you have any? What kind of things you follow in proving of theorem 1? Because according to that, what is given here in this formulation, this is trivial. Maybe something else should be given there.
Yes, Prof.
Do you understand my question on it? Because this one is upper, HK equals KH. Correct? It is not only in your example too. It is in general. HK equals KH. Since HK equals KH, that means union and intersection, because it is they are equal. So will be the same, KH. Number of elements, KH will be equal to number of elements on denominator. So that's why it is just one. Correct?
Okay, sorry, it's blank.
Yeah, this is regarding theorem number 1. So theorem number 2, which you just presented. Can I get theorem number 2?
Sorry, I'm sharing, but it's blank.
Okay, so in theorem number 2, okay, let me take just again. I have some question in theorem number 2 also. The problem is you are taking some trivial case, because if you have subgroup of order P, since group itself is order 2P, so that means any subgroup of order P is normal subgroup. So that's why your theorem 2 is a corollary from theorem 1. Also is trivial. Because P is a half of 2P. But any subgroup of order is half of the order of a group is normal subgroup. So that's why there in theorem 1, you put hypothesis that the subgroup is normal. So that condition holds in your second theorem also, because your subgroup of order P. So that's why it is normal. So it's an immediate consequence of theorem number 1. But theorem number 1 is trivial.
Okay, but I will look into this. I cannot show you here because the file is in other laptop.
I see. So
You may.
Another question regarding that probability degree. Probability degree, you are taking pairs for groups, not relatively probability degree, just probability degree. Probability degree, you are dividing by twice the order of group. You can just take all ones in the Keller table, number of ones in the Keller table, and or more precise, half of that, because you are taking pairs, one there and one here. So you're putting two ones. In fact, you can put one there and divide by the order of the group. That will be the same what you are defining there. Okay? This is number 3. Number 4. Another question is, in fact, that probability degree or your productivity degree depends on, must depend, at least, I'm sure, I believe it, must depend on the order of the group and the order of the subgroup. What is the relation? Because you have a probability degree, but in your case, it's 3/5. Maybe you just giving some particular cases, because it must depend on the order of your subgroup and the order of your group. Because definitely it is clear that it must depend on the order, because group is large, then productivity degree must be less, because more chances to be on the numerator. Something is not clear. Whatever, I don't know. That productivity degree is defined by whom? And it's Nurhaniza.
Yes. Sorry, Prof.
It is given by Prof. Nurhaniza, or
which probability?
Productivity degree.
Oh, we introduced that probability. You
introduced it because last time I remember that commutativity degree.
Mm-hmm.
I remember that a few 10 years ago, I think. Prof. Sarmin gave some talk. Nurhaniza Sarmin. Then I remember at that time is probability degree. I asked the same question from her. I didn't get answer. So that's why I am asking you as a her PhD student. So you should give at least answer for that probability degree. But that one is a productivity degree is something different than a probability.
Different, yes. Thank you, Prof, for the comments.
Thank you. But think about this. Productivity degree, since you are taking two groups or group and its subgroup, it must depend on the orders of group and its subgroup. That must be relation between that probability degree, that P must depend on NEK, where N is the degree, the order of group, and the K is the order of subgroup. Then, moreover, why you're taking dihedral group? So a lot of finite non-commutative groups, even that maybe for commutative group, for abelian group is always one there. I think so, huh?
Yes, because
for abelian groups, maybe it is always one. But a lot of non-abelian finite groups, except for dihedral groups. Say symmetric group you have, then say alternative group, and so on. Maybe just you should look at that as in your research, maybe your further.
But that degree is the most easier to
Which
determine,
one?
actually.
Which
the
one?
dihedral groups. I think the dihedral.
No, I know, but the dihedral, because it is simple to deal with dihedral groups, so that's why you dealt with that. My suggestion is take more complicated groups.
For other groups.
That will be research. For dihedral groups, looks like it is trivial. Say how to do it for symmetric groups or subgroups of symmetric groups, alternative group or some other groups. It's not so clear. For dihedral groups, it looks like more and less clear because dihedral groups structure is too simple. Just you have a cyclic group of half of the group and one subgroup of order 2. So that's why my suggestion is just look at for the same question, maybe for symmetric groups.
Okay, Prof. Thank you.
You're welcome.
Okay, Prof. Thank you for your great suggestions. Okay. Any more question from the audience? Any question? Maybe Sidek, maybe have a question, Sidek? You still Sidek?
Ya, Dr. Agus.
Question? Maybe you want to ask a question?
Okay, bolehlah nak tanya satu soalan, Dr. Miza.
Boleh.
Just a simple questions lah. I think your students, FYP student, I think for this semester dia buat lebih kurang benda yang sama lah. Cuma ada some things yang mungkin student dia tak clear lah. For example, you mentioned about the order of apa tadi? Macam mana you define that order of apa nama tadi? The order of dia punya, because saya tanya student tu because symbol yang guna tu symbol is like
Direct group betul?
Yes. Cuma the student tu dia tak boleh jawab. Bukan dia tak boleh jawab, dia jawab is like macam the order tu, I tanya dia how do you define the order of that thing? So dia kata the order tu is like finding the determinants.
The number of element dalam group tu lah.
Just the number of elements lah kan?
Yeah.
So it's depend on the number of the elements lah. Okay.
Yeah,
so because that student tu dia mungkin define.
Dia tak jawab.
Dia define, dia salah lah dia. So bila tanya betul ke benda tu symbol of determinant, so dia kata determinant betul. Tapi actually dia adalah just a number of element in that group lah kan. Okay, alright.
Okay.
Yeah, in fact, sorry. May I give some comments on groups? Because any finite group, Dr. Siddiq, is can be given as a symmetries of some figures. Say, if you take square that or n gone. If you take square, you will get dihedral group D2, and that is the notation. If you take n gone, then if you consider all symmetries of n gone, then you will get dihedral group of order 2n. You have rotations and reflections. So that's why combining them, you can get all elements of dihedral group. What Mohaniza just now showed us, in fact, can be given geometrically. Just taking n gone and they start to rotate it and deflect with respect to some axis. So that in the dihedral groups case, it is easy to have to find the table of multiplications and the number of elements, the order of group, and then how to describe. Even for the dihedral group, it is to describe all subgroups. That is such a very simple, more and less simple group. Okay. All right. Thank you.
Okay, thank you, Prof. Any more question, class? Any more question from the audience? Ada soalan? Kalau ada soalan, kita masih ada lagi lebih kurang 11 minit. Ataupun ada isu-isu nak dibangkitkan ke? Yang isu yang bersesuaian di dalam Kolokium ni, kalau ada apa nak dibangkitkan. Maybe KPP, anything you want to ask, or any issues you want to raise up, KPPs, Dr. Sumarni. Okay, jika tiada apa-apa isu untuk dibangkitkan, jadi terima kasih banyak-banyak kepada Dr. Muhammad kerana memberi kerjasama yang sangat baik dalam menjayakan Kolokium kita di petang ini. Okay. Jadi kita tangguhkan Kolokium kali ini dengan